we'll start this first lesson with a bit of a review of the trigonometry you've seen in previous years. We would have covered some harder stuff than this in year 12, but before then you would have seen that the SOHCAHTOA, right-angled triangle, has three sides, and its relationship between those sides can be broken down by sine, cos, and tan. Sine being the opposite over the hypotenuse, cosine being the adjacent over the hypotenuse, and tan being the opposite over the adjacent. Now it's just the relationship between those two sides that each one of these sine, cos, or tan trig relationships defines. So here's a graph of the sine one, which is as the angle changes, how does the opposite divided by the hypotenuse change? Cosine, which looks very similar but along a little bit, and the last one here being the tan graph, the opposite divided by the adjacent. So as the angle changes, or at particular angles, you can work out the relationship between the two sides using sine, cos, or tan. So here's an example. I know an angle, 30 degrees. I know that this side here, 5, is the hypotenuse, and the opposite, x, is the one we don't know, we're trying to find out. So the opposite is equal to divided by 5 will be 0.5, because sine of 30 is 0.5. So therefore x has to be 2.5, and we found out the missing side. So here's another triangle with one side 2.5 and another side 10. This time we're going to try and find out what is the unknown angle. So we've got the opposite and the adjacent, so we're going to use tan, TOA, and we're going to use an inverse of tan, which then takes the relationship between the two sides and gives you out an angle. This is not to be confused between inverse tan and 1 over tan, because this negative power of 1 does not mean 1 over in this particular case. We'll come to this later. This is backwards version of tan. This is the inverse, well, the reciprocal on the other side. So this tan to the negative 1 just does the opposite function rather than 1 over the function. Right, so looking at the sine graph, here's a graph which shows you that sine works out the relationship between this opposite and the hypotenuse at different values of the angle. So if you think of the angle as just a variable, or your x-axis, then as that angle changes, the relationship between the opposite and the hypotenuse will also change. And of course it just starts to repeat, and the angle goes on and on forever. Okay, we'll have a look at some of the features of these trig graphs now. So here's your normal sine graph. Now this graph can be described in terms of its period, its amplitude, and its frequency. So the period is how long it takes before it starts to repeat itself. So for a sine graph, that's 1 revolution. Just your basic sine graph, that's 1 revolution, or 360 degrees. Now the amplitude. Now imagine you are in the water at the ocean and a wave comes along. There's your wave. The amplitude is how far up from your resting point you move when the wave comes along at your maximum. Right? So in this case it's the opposite divided by the hypotenuse at its maximum is when the opposite is equal to the hypotenuse, and it's 1 or negative 1 down this way. So the amplitude is how far you go from the middle of the graph to the maximum or the minimum. Last thing, the frequency. Now frequency is how many times something happens, and in this case we're talking about how many times does the graph repeat itself in 1 revolution of a circle. So the frequency for your basic sine graph is 1, amplitude is 1, and the period is 360 degrees. Okay, we're going to look at how we can edit these graphs or change them from the basic graph that we saw before into whatever we want, really. So the period of your sine graph is at the moment 360, so there you have the 360, and the amplitude is 1. Now if I change this coefficient value at the front A, then you can see making it bigger changes the amplitude to whatever you want it to be. So I made it 2, now I'm just moving it around. You can make it negative if you want, and I'll bring it back to 1. That just changes the amplitude. The next thing I'll do is I'll put in another number here, we'll call it B, to just multiply inside the sine function. So here we're multiplying the angle that the sine function takes in, As you can see, if I increase that value, then what you'd expect is maybe not what you get. When I multiply, make it bigger, the graph actually compresses. Okay, so what's happening is it's taking in an angle, for example, say 30 degrees, then the sun function's reading that as 30 degrees times 2, that's the value I put as b is 2, so now it's really thinking what is sine of 60 degrees, which is twice as far along, so that's why it's compressing it. It's doubling the angle, and it's reading it as double what the original angle was, so the graph is now happening twice as often, and you can see that the period inside the 360 degrees, the frequency is 2 now, because the period is only 180 degrees, so it occurs twice inside the 360 degrees, or one circle. Now, the next change we'll make is to put another number here, just an extra coefficient here, c being the number that we add to the angle that the sine graph reads. So this is all inside the sine, and if you remember back to when we did parabolas, if you had a parabola and you wanted to shift it to the left, say, well, if you added a number on here at the end, whatever it is, just C, the one we were using before, you would shift it up. If we wanted to move it along, we had to put it inside the brackets. In this case, it will move it to the left by adding a number on. So what that's reading is your angle 30 degrees plus 1, it's now reading 31 degrees, which would have been just a little bit to the right, so it actually shifts the graph to the left. Here's some, I'll just make this coefficient a bit bigger, I'll make it 5 times whatever C was, just so you can see this happen a bit more obvious. If I increase the value, it moves it to the left, and it seems to move it to the left, which is perhaps counterintuitive, but it's what happened with this the quadratic graphs last year. Right, the last one to change will be this final one we put at the end. Now it's outside of the brackets, so all it does is shift it up and down. So it doesn't change the graph in any way except for moves it up by however much you put in for the d value. Sine is an operation. It works just like the rest of the order of operations, so it's sine of whatever in the brackets, and then you multiply it, and then you add the d value on at the end. Right. Next thing we'll look at is degrees and radians. We all know there's 360 degrees inside a circle. Degrees are just a unit of measuring angles, and so are radians, just the same. Now, degrees and radians, deg and rad, written like that on your calculator, will help you change between the two different functions. I think function on most calculators will get you there. There's a relationship, of course, between the circumference and the diameter of a circle. Circumference equals pi times the diameter. The diameter is equal to double the radius. So therefore the circumference is equal to 2 times the radius times pi. So the circumference, or a rotation of 360 degrees, is equal to 2 pi times the radius. So here we go, here's a unit circle, radius 1, rotating around 360 degrees. Alright, we'll say it again, it rotates 180 degrees, and as you can see, one rotation is equal to 2 pi, so 360 degrees is equal to 2 pi times the radius. If you laid out a bit of string as it rolled along, 2 pi is equal to 360 degrees, so 2 pi radians is equal to 360 degrees. Pi, being just a number, so don't forget, pi is 3.14, so pi is equal to 180 degrees, so 3.14 radians is equal to 180 degrees. 3.14159.8. I can't remember any further than that. I don't even know if that's right. Guess the film. It's like picturing. Life of Pi, yes, that's right. Had that film ruined for me. Who lets their kid bring a Bluetooth speaker to the movies? I don't even know why that was a good idea. Anyway, so 1 radian is a unit of angles, same as degrees. Right, so here you can see a radian is, if you took the radius and you took that distance and you looped it around the side of the circle, the angle you've turned is equal to 1 radian. So it's 1 radius as a trip around the side of the circle there. Okay, so why do we even use radians, or why would we use radians instead of degrees, or the other way around? Well, here we've got a sine graph written out again, and as you can probably see, the distance it travels is about 6 point something, or 2 pi. So let me just fix this up so it looks like it should. Right, because degrees are smaller, there's a lot more of them inside a circle. So if you're converting between radians, which I was originally on, to degrees, you need to divide by 180 and multiply by pi, because the relationship is pi is equal to 180 degrees. So I multiply by pi, divide by 180, and that gets me a graph which is now between 0 and 360, and I just adjust it so you can see. But now the reason we would use radians, well, look at this. The x-axis goes from 0 to 360, the y-axis goes from -1 to 1, so it's not exactly very good scale. And that's it.